Hello, my name is Jacques, and today we're going to continue learning the basics of the Bevy Game Engine. Bevy is a simple data-driven game engine built in Rust. It's free and open source. This tutorial is the 8th episode in my Learn Bevy 0.10 video series. This episode builds on what we learned in the previous episodes. If you've been enjoying this series and finding it helpful, please consider subscribing and sharing it with your friends that would also be interested to learn how to make games and join the Bevy community. Today, we're going to be continuing with our Bevy ball game project we've been working on. In today's episode, we're going to be learning explicit system ordering and system sets. These are two invaluable tools to have in our Bevy tool belts. Explicit system ordering and system sets give us absolute control over the order in which our systems are run. Let's hop back to our code and get started. When we run our project, you may have already noticed a strange artifact. When we move our player up against the edge of the window, we see what we expect. The player sprite stays perfectly within the window. This is the behavior we want. But other times, you may have already noticed, we see a brief bounce back effect where the edge of the player sprite goes outside the window and then one frame later is moved back within the window. What's causing this behavior? It's due to the order that our player movement system and our confined player movement system are run in. Remember, Bevy systems do not run in a specific order by default. Just because we wrote add system player movement before add system confined player movement doesn't mean they're getting run in that order. The order systems are run in is non-deterministic. What does non-deterministic mean? It means that for every input there can be many different outputs, or put another way, likely to have a different result each time. This is due to Bevy's system scheduling algorithm. Bevy's scheduling algorithm takes all our system function signatures as input, looks at what data each system wants to read or mutate, whether the data comes from queries, resources, or using commands, and from this information, the scheduling algorithm creates an order for our systems to run in as its output. This means that not only is this order potentially different for each run of our game, it can be different for each frame of our game. This is why sometimes we see the bounce back effect, and sometimes we don't. This is a case where we need to explicitly tell the Bevy scheduling algorithm we want to run the confined player movement system after our player movement system to ensure we get the behavior we want. To do this, we use explicit system ordering. Let's hop back to our code now and see how we can use explicit system ordering to solve the bounce back effect problem. The solution is quite simple. We call the before method on our system inside our add system method. Player movement dot before, and then as the parameter here, we're just going to paste in confined player movement. And that's all you need to guarantee that the confined player movement system will run after our player movement system. Bevy also provides a .after method. Instead of using this before method, we can also say confined player movement after player movement. And this will have the same effect. Having both before and after won't change the behavior and is unnecessary. We just need one. It's up to you to decide which one you want to use based on the context of your situation, but the behavior is the same. For this particular situation, I think it's best to use the after method, so I'll remove the before method, and I think that just reads a bit better in the English language. Confined player movement after player movement. That makes sense to me. Another way we can organize our systems here and explicitly tell one system to run before or after another is to use a slightly different format here. Instead of using add system and adding these individually, I'm going to use the add systems method. Inside here, I first need a tuple so that I only pass it one argument. And we'll start with the player movement system as we did before, comma, confined player movement. With the shorthand, I'll now write after as we did before, after. So this code is equivalent to the previous one, but it kind of nests the logic a bit more to keep it clear and concise. Bevy provides one more shorthand we can use here. If I remove .after here and simply on my tuple that contains player movement and confined player movement, I can call .chain. .chain runs the systems that you have in sequence and will have the exact same effect to ensure that player movement runs before confined player movement. or rather, confined player movement runs after player movement. So those are 3 ways you can achieve the same effect to explicitly order your systems. A word of caution with explicit system ordering. In most cases, it's fine if you have to wait 1 frame for a system to run that depends on a previous system performing some behavior. Be aware of overusing explicit system ordering. The more you explicitly order your systems, the more you take away opportunities for the Bevy scheduler to run your systems in parallel, and you'll lose performance as you force systems to run sequentially. Explicit system ordering is a tool in your tool belt, and if you're using it for every system, you're probably doing something wrong. Remember, by default, all systems run in parallel unless they require mutable access to the same data. Recall from the first episode, parallelization is one of the reasons why Bevy is so fast. These 2 systems, the player movement system and the confined player movement system, aren't run in parallel regardless of how we order them, because both player movement and confined player movement both require mutable access to the player's transform. So here, explicit system ordering doesn't have any impact on performance whatsoever. It's the same as it would have been without it. Another good example of where explicit system ordering would be great to use is with game over logic, where you probably want to check for your game over condition after all your game logic has run, so that you can end your game and not have the game run for an additional frame after you've discovered it's the game over state. Another more advanced way we can order our systems is by using system sets. System sets are a Bevy concept we can use, as the name implies, to create sets of systems. We can create a set, let's say system set A, and place 1 or more systems in that set, and then let's create another set, let's say system set B, that we place other systems into, and then finally we can tell our app to run set A before or after the other set B. Let's take a look at this now with our player movement and confined player movement systems. Here above my plugin, I'm going to create the following system sets. I'm creating pub struct movement system set, which is just going to be an empty strut, and another one, confinement system set, which is another empty strut. Now, to tell Bevy that these are system sets, we're going to need to derive the system set macro, similar to how we derived component and resource. Above our movement set struct, we derive system set. But in order to get the full functionality of system set, we're going to need to derive a couple more traits to make this trait work. In this case, we're also going to need debug, hash, partial EQ, EQ, and clone. Now, explaining the rest of these is outside the scope of this tutorial, but just know, for this one to work, we also need these ones. It's as simple as that. Let's add the same derive statement above the confinement system. Oh, I forgot to call it set there. I'm calling it set just to be explicit here. And there we go. We've declared both of these to be system sets. Now, similar to how we told Bevy that we're adding resources or events, we need to also tell Bevy that we want to add these system sets. Here, in my player plugin, before I add my startup systems, I'm going to say configure set. Inside here, I need to set the rules that I want to apply to these system sets. I want my confinement system set to run after my movement system set, or the other way around, the movement system set to run before the confinement system set. For this example, I'll just say movement system set before confinement system set. And that's it. Any system inside this movement system set will run before the systems in the confinement system set. We're going to now need to add our player movement system to our movement system set and our confined player movement system to our confinement system set. We're going to get rid of this line and go back to adding them individually. Add system player movement dot inset movement system set. Same thing for the confined player movement system. Add system confined player movement system inset confinement system set. And there we go. We've accomplished the same thing, just using system sets. Now, you can get really complex with system sets. You can make your system sets into enums, For example, we could have made one system set with different enums. Let's ignore that for a minute. For example, we could have created a player system set enum and made one case movement and another confinement. We'd need to change this logic to now use our enum instead. We need to use the same derive macro here above it, and then we need to change these to use the enum values instead, just like that for our configure set method. And here we'd use the enum values, and then again, exact same behavior, just doing it a different way. Again, you can get really complex behavior with system sets. We could also nest sets inside other sets. We could add the same system to multiple sets. It's a very, very powerful tool in our Rust tool belts. But for now, this is as much complexity for our beginner project as we want. And honestly, for this project, we were perfectly fine without system sets. I just wanted to teach you this as an example. For this project, we were really fine just using the original .before and .after methods on our systems to achieve our explicit system ordering. But I want you to know that system sets exist, and they're a very robust and powerful way to order and group your systems. We'll see in the next episode as we cover state, how we can easily run or ignore systems using a combination of system sets, run criteria, and state based on the current state of our application. For now, I'm going to undo what I did, and I'm going to use this kind of like intermediate example we had where we were just using two system sets that were each just empty struts, adding them here. I'll add a comment there just to keep it clear, where we were using a very basic example of system sets to achieve explicit system ordering. Again though, for this project, you could honestly just go back to using the original .before and .after methods on our systems. That brings us to the end of episode 8. We've covered explicit system ordering and system sets. This episode hasn't been very code heavy, but it's been rather concept heavy. Still to come are states, fixed time steps, UI, and many more examples. Thank you all very much for watching. Please post your questions and any feedback down in the comments below. Thank you all very much, and see you in episode 9.